Good morning. So we started out with some warm-ups of composition, so that we are composing both ways. And I did the first two where I composed, and on A, what I did when I composed both ways, I got an X. But when I composed both ways on B, I either got this x squared minus 6x plus 1, or when I composed the other way, I got negative 3x squared plus 6x minus 1. The reason we started out with the compositions of functions is because today we're going to be finding inverses. And we have a rule that says when we compose both ways, my answer had only better be x. If I compose both ways and my answer only is x, then we're going to find that they are inverses of each other. So let's explain what an inverse is and determine whether or not functions can have inverses or not. So first we have to talk about whether or not it is one-to-one. Now we talked a little bit about one-to-one at the beginning. I think it was like 1.2 or 1.3. When we were talking about functions, we were also talking about one-to-one functions. We talked a little bit about it then, but now we're really going to talk about it. And what a one-to-one function is that for every x, there's only one y associated to it, and for every y, there's only one x associated to it. So that means that I don't have repeats on y's when I write out my range. And of course, I won't have repeats on x's because otherwise it won't be a function. So if I have a graph, what one-to-one means is it has to pass first the vertical line test because that makes it a function. Now it has to pass the horizontal line test, so it makes it one-to-one. So as an example, if I were asked to determine whether or not this is one-to-one, then I would just draw a horizontal line. In this case, my horizontal line actually touches it twice. So I know that this is not one-to-one. So if I want to be able to find the inverses of these two functions, then I have to do something what we call restricting the domain. So if I want to cut the domain in such a way that I get all of my possible x or y values, so I want all my possible range values. So if I decide I'm going to cut my domain right here and I say, okay, I want my domain to be restricted from inclusive of, say, that looks like it's about 1.7 to infinity, then I'm only getting these values of my range. So when I restrict my domain, I want all the possible range values. Now, if I restrict it right there, and then I'm missing all of these in green. So I'm not going to cut it there. I'm going to cut it, and we're going to discover what this is called. It's called the vertex. When we get into quadratics in chapter 3, we'll call that the vertex. So what I do when I have a quadratic, which is when I have a power of 2 and it has this shape, then I'm going to cut it at the vertex, at the very bottom or the very top. So from 0 to infinity. Now the red line is one-to-one. So go ahead and take a look at B, and in the chat window, determine where you're going to cut the domain on B to ensure that it is one-to-one and you get every possible range value. The second one, the assumption is that these are going up forever, and I need to cut it at that turning point so I get all possible outputs. So option A, and there are two options. On this one, on A, what I did on A was do you like that? I chose this side, but I could have easily have chose this side. The same thing is going to be true here. Is either I'm going to choose this right-hand side or I'm going to choose this left-hand side. But I'm going to start it down here at 2, just like here I started it at 0. So my other choice for this one could have been from negative infinity to 0. Got to make sure you include 0. So that means over here I can go from negative infinity to 2 inclusive, or that takes the left side, or I could have gone from 2 to infinity. That takes the right side. So you're going to choose which side you want. And there's going to be times in which you'll want to choose the left-hand side. There's going to be times when we want to choose the left-hand side or the right-hand side. Typically, I will choose the right-hand side so that I can work with positive numbers, but that doesn't mean that it's always going to be that way. Typically, though, I will choose the right-hand side. Any questions so far? Yeah, that is a lightsaber, because, I found that the other day. I'm like, ooh, I've got to use that. I got different colors on that too. All right. What about this one? Where would you cut this one? Let me make this larger. Where would you cut this one to get all the possible outputs? So I can cut it on the right-hand side, or I can cut it on the left-hand side. So my domain I'm going to restrict it to is either from 0, inclusive, to 2, non-inclusive, union from 2 to infinity, or from negative infinity to negative 2, union with negative 2 to 0. So either I take the left-hand side or I take the right-hand side. It really is up to you. If they don't ask, then we choose not to. We choose the positive is usually the easier one, but you can choose the left or the right. Now, what happens with these vertical asymptotes, and we're going to go really into depth on those later in this quarter, these are vertical asymptotes. So if you remember, when we had something like this where we had some kind of numerator, and in the denominator we said x, so we had x squared minus 4, and we said, oh, the domain restrictions are as x cannot be positive and negative 2 when we factored. That's what happens when we pull out values, which we're going to learn more about later in this quarter, is when we pull out those domain restrictions, it ends up becoming vertical asymptotes. How are we doing? Any kind of questions? So let's talk about inverse functions. So when we're talking about an inverse function, what it means is that when I compose both ways, and notice that this is the first time we've seen this notation, this means inverse. This does not mean 1 over f of x. It means when I see this f inverse like this, that means I have the inverse function. That means when I'm talking about inverses, it says I have the answer. Whenever I see an inverse, it means I have the answer, I have the range, I have the y. What x was put into my function to get that y value. So what we're doing with inverse functions is we are undoing the function itself, and it says I have the answer. What input is associated to this answer? So if it's 1-to-1 and I found an inverse, then when I do my composition both ways, my answer is just x. So if I come back up to my my warm-up up here, noticed how my very first one, let me see, I'll do red this time. So this was x, and this was x. So by definition, these two functions are inverses of each other. So I can write this as f of x is equal to x plus 3, and f inverse of x is equal to x minus 3. So if g of x was actually the inverse. But when I take a look at this, I ended up with either 9x squared minus 6x plus 1, or I ended up with negative 3x squared plus 6x minus 1. So that means that these are not inverses of each other. So inverse functions have to, when I do composition both ways, they have to equal just x. And this one didn't equal just x, and this one didn't equal just x. So they know that those are not inverses. So when we are doing inverse functions, the first thing we have to do is determine if my original function is 1-to-1. If my original is 1-to-1, or if it's not, I can always restrict the domain. If it's 1-to-1, then I try to find the inverse, and then the last thing I always do when I think I have the inverse is I always do this last. I always compose both ways to ensure what I really have are inverses of each other. So we come back and we know that this one is yes. We know this one is no. I'd like you all to try these two and determine whether or not they are actually inverses of each other. So go ahead and compose both ways on C and D and determine whether or not they are inverses of each other. Okay, let's go ahead and go through C and D. We're going to compose both ways. So first I'm going to do f composed with the g of x, which is f of the square root of x plus 3, which is equal to square root of x plus 3, the quantity squared, minus 3. So this, when we square a square root, we just get what's underneath the square root, what's underneath the radicand. So x plus 3 minus 3, so we get x. So that checks out. And then g of f of x is equal to g of x squared minus 3, which is equal to x square root of x squared minus 3 plus 3, which is equal to square root of x squared, which is equal to x, and that checks out. But these are not inverses of each other. Why are they not inverses of each other? They're close, but they're not truly inverses of each other. Why are they not truly inverses of each other? And that's because what happens when I graph C, when I graph f, this is what f of x looks like. So I'm going to come all the way down here to 0, negative 3. So that's what f of x looks like. So f of x isn't 1-to-1. Because it's not 1-to-1 without a restricted domain, they're actually not inverses of each other. So for them to be inverses, you would have had to say x. You'd have to say your domain x such that x is greater than or equal to 0, or interval notation. If you would have had that caveat in there saying that I restricted my domain, they absolutely would have been inverses of each other. So they check out, but they're not inverses because C does not have, on f of x, it's not 1-to-1 to begin with, so they're not truly inverses of each other. If they would have been restricted domains, they absolutely would have been. Okay, so let's look at D now. So let me bring this down here. So when we take a look at D, I'm going to do f composed of g of x, which is f of 1 over x plus 1, which is equal to 1 minus 1 over x plus 1 over x. Now what I'm going to do is I'm going to look to see what my lowest common denominator of all my fractions are within my nested fraction. My lowest common denominator is x plus 1. So I'm going to multiply this by x plus 1 over 1, this by x plus 1 over 1, and this by x plus 1 over 1. And what that'll do is it'll allow me to clear my fractions. So this is going to be equal to x plus 1 minus 1 over x plus 1. In my numerator I get x, and then here x plus 1. And so I end up with 1 over x plus 1. This does not equal x, so these are not inverses. So as long as one of them doesn't check out, you can stop. You don't have to continue on and find whether or not it checks the other way. Provided one doesn't check, then it doesn't matter if the other one does. So as long as one doesn't check, it is not an inverse of each other. All right. What other kind of questions do you have for me? Questions, and we're going to go on. So what happens when we do inverses is domains become ranges and ranges become domains. So when I have something that looks like this, f of x is equal to 2x minus 1, and say I put in 3, then I have 2 times 3 minus 1, which gives me 6 minus 1, which gives me 5. When I have an inverse function, what I put in isn't 3 as I put in 5. So I have the answer. Notice how this is my range value. My range becomes the input. So it is at this moment when we do that solving for x, which we'll be doing in a minute, is when my domains become ranges and my ranges become domains. So my output in my original function was 5. That's what I put into my input on my inverse. So when that happens is that my graph of my original function gets reflected over the line y equals x. This is the line y equals x. So if the point 4, 2 or 2, 4 is in my original function, then it gets reflected over to 4, 2. Notice the x's and y's change position. If I have the point negative 1, 3, then on my inverse, it becomes 3, negative 1. So come back up here to my example. If I put in 5 into my inverse, 3 had better come out, because my original function had 3, 5 as my ordered pairs, but for my inverse right here, it becomes 5, 3. Domains become ranges, ranges become domains. So, if we are asked to find the domain and if we're asked to find the inverse, there are certain steps that we take to make our lives easier. First thing we want to do is make sure it's 1-to-1. The reason we want to make sure it's 1-to-1 because if it's not, it won't have an inverse. We may have to restrict our domain here too, so you may have to restrict domain. One slash one is the quick way of writing 1-to-1. So you may need to restrict the domain to ensure it's 1-to-1. Then we place f of x with y. And the reason we do that is because it's easier notationally to say instead of writing f of x everywhere is to write y. Once we have replaced f of x with y, we solve for x. Now, you'll see some videos that say switch right at that moment. Number 3, switch f of x with x, y with x. I don't care for that. And the reason I wait till the very end to do replacements, as you can see, 4 and 5 as replacements, is because one of the skills that you'll need in calculus is to be able to solve for y, because there's going to be times in which we do derivatives or when we integrate, it's in respect to y. So in other words, y is the independent. So getting the ability to solve for y and solve for x and not y is a tool that ideally everyone would have coming into calculus. So if you watch other videos, cool. Just note that I do that replacement at the very end. The videos usually do it right out of the gate. I don't. Okay, so then I solve for x. Once I solve for x, I replace x with f inverse of x, and I replace y with x within my f inverse of x, my inverse function. And then that way I'm only working with x. And then I have to check the composition. So step 5 here is that moment my domains become ranges and my ranges become domains. And it is not possible to have more than one inverse because each inverse is unique to the function that you started out with. So here's 3 of them. A, B, C, and D. Which one of these, if you can see them, which one of these would you like me to do? Because you all are going to do the other ones. D? B? B? Okay, I'll do B. So when I take a look at this, and I'm trying to determine if this is 1-to-1, the first thing I do is I write y is equal to 2 over x plus 3. And I ask myself, if I put a value in for x, will this have more than one output? And the answer is no. Every time I put in one singular x, one singular y will come out. So this is 1-to-1 to begin with. So this is 1-to-1. So if it's 1-to-1, then if I look at this and I say I have no idea how to draw this, the first thing we do is we say, what is my restricted domain to begin with? My restricted domain to begin with is that we know it can't be -3. So it's going to go from -infinity to -3, union between -3 to infinity. And that's because x can't be -3 in the denominator. Once I find the domain, without doing any work, so if this is the domain of my function, without doing any work whatsoever, this becomes the range of my inverse. So I don't have to do any work. I know what that is. Now, if I don't know what this graph looks like, then I'm going to come over here and do some ordered pairs. So x and then f of x. So I might choose, I can't choose -3, so I might choose -4. Actually, let me start with -5. -5, -4, can't choose -3, so then maybe -2, -1, 0. So I'm going to put -5 in there, so I have 2 over -5 plus 3, which 2 over -5 plus 3 is -1. So I'm going to draw my graph here. And when I put in -1, actually, I'm going to move this y over a little bit. So when I put in -1, or -5, -1 comes out. So 1, 2, 3, 4, 5, -1. Now, for my inverse function, I know if that number is -5, -1, then -1, -5 should be 1, 2, 3, 4, 5. 2, 3, 4, 5. Should be on the inverse. So then I put in -4. So 2, -4 plus 3 is -2. So I have -4, -2, -4, -2. That means my inverse function should have a positive, or should have a -2, -4. So -2, -4. So as I find my function here, I can plot my inverse function points at the same time. Now, my original function, I had a restriction at -3. So x equals -3 is the restricted domain on my original function. But remember, that becomes a restricted on my range. So on my range, my inverse, it is y is equal to -3. So if we have a vertical asymptote on my original function, it becomes a horizontal asymptote on my inverse. Okay, so let's keep trying -2. So I put -2 in there. So I have 2 over -2 plus 3, which gives me 1. So on my original function, I have -2, 1. So here's -2, 1. That means on my inverse function, I have 1, -2. So I have 1, -2. So that's where my inverse function is. I put in -1, so 2 over -1 plus 3. So what comes out is +1, so -1, +1. Let me see. Did I do that right? So I put in -2, I get 1. I get 2. That should be 2. So let me erase that. That should be 2. So I put in -2, -2, or +2 comes out. If I put in -1, +1 comes out. And so this is what the graph of my original function looks like. It's going to look something like this. And then on my inverse function, when I put in -2 and 2 came out, on my inverse function, +2, -2 came out. So +2 and -2 came out. And when I put in -1, 1 came out, so 1, -1. So my inverse function is going to look something like this. And let me see, it's going to look something like that. So that's what my inverse function looks like. So let's come back over here and actually do the inverse. So we're going to go through the steps. Y is equal to 2, x plus 3. Now we know it's 1 to 1. For every x I put in, only one y comes out. And then what I'm going to do now is I'm going to solve for x. So I'm going to multiply both sides by the x plus 3. When I multiply both sides by the x plus 3, I'm going to get y. X plus 3 is equal to 2. Option A is I distribute the y. Option B is I divide by y. I'm going to go ahead and distribute. So I get xy plus 3y is equal to 2. Anything not attached to the x, I'm going to move to the other side of the equal sign. So xy is equal to 2 minus 3y. Now I'm going to divide by y. And I've got x is equal to 2 minus 3y divided by y. My last step is to replace f of x, or f inverse of x with x and y with x's. So at this moment, f inverse of x is equal to 2 minus 3x over x. It is at that moment that my domains become ranges and my ranges become domains. So I know what my domain of my original function was, and that gives me my range of my inverse. Based on my graph, I can tell you what the domain of my original function is, or my range of my original function is. The range of my original function is from negative infinity to 0, union between 0 and infinity. Now, here's the thing. If I did not know what that range was, that's okay, because I can find my inverse and I see my restriction on my inverse, and my restriction on my inverse is it can't be 0. So I can graph them, which is being able to graph them is something that we need to know how to do. But if I didn't, I can find my inverse and then do that, and then find the restricted domain of my inverse. That is the range of my original function. Domains become ranges, and ranges become domains. It is at this step right here that my domains and ranges switch. So notice the domain of f is the range of my inverse. The range of f is the domain of my inverse. Now all I have to do is I need to check these both ways. So I'm going to check them by the composition f of f inverse of x, which is equal to 2 over 2 minus 3x over x plus 3. Multiply everything by x because that's my lowest common denominator, so multiply by x over 1 everywhere. And so I get 2x in the numerator. I get 2 minus 3x plus 3x, which is equal to 2x over 2, which is equal to x. So that works that way. And then I have to check the other way. So now I'm going to check the other way. So I'm just going to come over here and check the other way. So f inverse of f of x is equal to, let me see, my inverse was 2 minus 3 multiplied by 2 over x plus 3 over 2 over x plus 3. Now I'm going to go ahead and multiply everything by x plus 3, because that's my lowest common denominator, so x plus 3. So this is equal to 2, x plus 3 minus 6 over 2, 2x plus 6 minus 6 over 2, 2x over 2, x. So I did indeed find the inverse of the function. Now I'm going to stop because I did a lot of work for just one problem. I'm going to ask you, what kind of questions do you have for me? You can unmute or you can just type it in the chat. Turn the record on. So the first thing we do is replace f of x with y, and then we subtract 5 from both sides, and then we replace x with f inverse of x is equal to, and replace the y with x minus 5. The domain of my original function, because this is a line, is everything. The range of my original function, so these are f subscript, is also everything because it's a line. That means my domain, or excuse me, my range of my inverse is everything, and my domain of my inverse is everything. Domains become ranges, ranges become domains. Now we just have to check this, so let's compose both ways. F of f inverse of x, which is going to be x minus 5. We're plugging that in wherever we see x here, plus 5, and we do indeed get x. F inverse of f of x is equal to x plus 5 minus 5, which does indeed give me x. So now let's just go ahead and graph these two. So my original function is a line with a y-intercept at positive 5. 2, 3, 4, 5. So it looks like this with a slope of 1, 1. So there's my original function. Now, my inverse is going to be reflected over this line y equals x. So if I had this point right here on my original function, which was 0, 5, then I must have 5, 0. 2, 3, 4, 5. So 5, 0 must be on my graph. If I had this point right here, which should be negative 5, 0, then this point, 1, 2, 3, 4, 5, should be 0, negative 5. And so my inverse is going to be over here. So domains become ranges, ranges become domains. How was that one? Okay. So let's take a look at C. Now, if I don't know whether or not it has an inverse, then I can always start solving for y and determine then. So determine whether or not it's 1-to-1. Let's just kind of deviate a moment and talk about what happens when we're not sure. So remember that one where we had f of x is equal to x squared minus 3, and we said they actually weren't inverses of each other? Let's take a moment and deviate from C and D, and we can always pick these up tomorrow. I have y is equal to x squared minus 3. So this is separate from all the rest of this. This is just another random example. So let's just work on this one. So when I solve for x, I'm going to get y plus 3 is equal to x squared. And then I'm going to take the square root of both sides. When I take the square root of both sides, right here, I have to slap on that plus and minus. It is that plus and minus that tells me that this is not 1-to-1. That plus and minus tells me it is not 1-to-1. Because it's plus and minus, it's not 1-to-1, and I can't find an inverse without restricting to the domain. And if you remember, we said, okay, if we restrict that at x greater than or equal to 0, then we will have 1-to-1, but otherwise, without that restricted domain, it is not 1-to-1. So going back to this one, we're going to do the same kind of thing. Y is equal to negative x cubed plus 2. And go ahead and solve for x on that and determine whether or not it is 1-to-1, please. So when we solve for x on C, we're going to do the same thing. We're going to add or subtract 2 from both sides. Now, the difference between this one and a squared is that when I take the cube root, you don't have to do the plus and minus. It's only when you have a square root or when you have a fourth root, when you have an even index, and you have to do the plus and minus. So I'm going to go ahead and divide by a -1 because of this negative right here. I'm going to divide by -1, both sides. What's going to happen is it's going to be 2 minus y is equal to x cubed, because the negative makes opposite signs, so the -1 makes it a -y instead of positive. Now I could have wrote this as well. I could have left it in the order it was in, which is -y plus 2. That's okay too. That's totally okay. Now when you do the cube root here, so the cube root and the cube root, you don't have to put the plus and minus on it. And so we're going to get x is equal to the cube root of, and I'm just going to write it as 2 minus y. And there, because I don't have the plus and minus, this is 1-to-1, so I don't have to restrict the domain of this to make it 1-to-1. So then f inverse of x is equal to the cube root of 2 minus x. Now, before we finish up today, I would want to finish this particular problem. The domain for this, to start out with, the original domain is -infinity to infinity. The parent function on this is the cubed function, and so we know there's no restrictions on that, which means I get the range of my inverse right out of the gate. And then because there's no restriction and cube roots is one of those ones that go from -infinity to infinity, my range of my original function is also -infinity to infinity. That means my domain of my inverse is also -infinity to infinity. And even if I didn't know that, I know that I can take the cube root of a negative number. So it's okay if I have negatives underneath there. Now, when I go to graph this, my original function is a transformed of the parent function x cubed. It is reflected over, so this negative reflects it over the x-axis. This positive 2 brings it up 2. So instead of going through 0, 0, it's going to go through this point right here, which is the point 0, 2. That means my inverse will go through the point 2, 0. Domains become ranges, ranges become domains. It's going to go through the point -1, positive 3. That means my inverse is going to go through positive 3 and then -1. So we'll go through that point. This is also going to go through the point, my original function is going to go through the point 1, 1, and so is my inverse. So here's what my original function is going to look like, something like that. And then my inverse function is going to look something like that. So it's going to be reflected over the line y equals x. So it's going to be reflected over this line y is equal to x. What kind of questions do you have for me? I know I should check it, and tomorrow we'll check it. All right. So tomorrow when I see you all, we will finish up with the inverse. There's an application. There is some answering inverses by pulling it out of tables, and we can also do it by graphs. And that will put our inverses to bed for now. And then tomorrow we'll probably pick up 2.1. I'm expecting that we'll probably have the test over the weekend. I'll open it up. I think we'll probably be done with everything and start new material by Friday. We'll see. If we finish everything by Friday, so if we finish, because we don't have much in 2.4, if we finish chapter 2 by Thursday, then I'll run the test from Friday to Monday. That way people don't have to do it over the weekend. They can start it as early as 12:01 a.m. on Friday. If we finish everything on Friday, then I'll run it over the weekend and on that Monday, so that you don't have to work on the weekend if you're not inclined. So you'll have time. And it will cover chapters 1 through 2, so 1 and 2. Does anyone have any questions for me? No. So you'll actually have a test. It will be generated in MyOpenMath. So there'll be a test in MyOpenMath, and I will put a review in MyOpenMath, and it'll probably be about, 30 to 40 questions, and you can do it or not. If you're in my Math 140 class, you have to do it as a grade. If you're not in my Math 140 class, it's just practice. So I'll put some review questions, not a practice test, it's review questions. So I'll put some review questions prior to the test in MyOpenMath, but the test will be in MyOpenMath. The take-home quiz is still due on Friday. So the take-home quiz is still due on Friday, one way or the other. The final draft is. Your first draft is due tomorrow morning at 8 o'clock. So your first draft is tomorrow morning at 8 o'clock for that take-home quiz. Anything else I can help you with? Okay, if you have questions, don't hesitate to ask. I do have a new link to office hours so that you don't have to sit in the waiting room. You can just come in and get your questions answered. If you are wanting to meet with me one-on-one, then there's a link for that as well. I believe I sent it in everyone's email. If I didn't, I did put it in the announcements. So the one-on-one is a certain link, and then my office hours from 12:30 to 2 today is the other link that's in there. Otherwise, you all have a great afternoon, and we will see you tomorrow finishing up inverse functions.